Okay, since you guys have your first test coming up, I wanted to give you a brief review of Chapter 1. Now, this review is not exhaustive, so these are the things that I think are the most important about Chapter 1, but you should also look at your lecture notes as well as page 35 in your textbook. Look at those key concepts. Read them over, make sure you understand them. Not only do you need to understand them, but you need to be able to apply that information in in solving a problem. And so the types of problems, right, you can look at the clicker questions, you can look at the homework questions for Chapter 1, and you can also look at the worksheets that you did in your recitation section. Those would be good places to get an idea of how that information needs to be applied. I will make a video for Chapter 2 as well, including some of those mass abundance types of problems that we solved on Friday. Okay, so this chapter is essentially orienting you to chemistry and giving you the tools that you'll need to solve all of our subsequent problems. So we know that matter is composed of atoms and molecules, and chemistry is really, at the most basic level, the study of matter and the properties of atoms and molecules. So an example of a molecule is carbon monoxide. Carbon monoxide is composed of a carbon atom and an oxygen atom. So atoms make up molecules. One thing that's important to me that you leave this class with is this understanding that we think about atoms and molecules in sort of two different ways. One way is at the particulate, so really small, at the molecular representation sort of way, and then also in this macroscopic sort of way. So when you hear carbon monoxide, you probably think, oh, okay, carbon monoxide is this poisonous gas that comes from cars. So that's one way to think of carbon monoxide. Another way to think about carbon monoxide is just to write its name. Another way is to do one of these space filling models. And remember, in this space filling model, we said in class that carbon atoms are going to be represented as black, oxygen atoms as red, hydrogen atoms as white. And so that'll help orient you to what you're looking at. We also said that we could write the chemical formula of molecules. So in this case, carbon monoxide would be CO. We said that we could also write the structural formula. In this case, it would be C triple bond O. And then we also said there was another kind of model, ball and stick model. So just keep that in mind as you're looking at these pictures in your textbook and in my lectures, so that you know what we're talking about. And then these sort of representations, we refer to those as representations at the particulate level. Okay, so we classify matter by its state and also by its composition. So matter is essentially anything that has mass and takes up space. So pretty much everything around you except for light. And just to illustrate how we classify matter, in class we talked about hydrogen peroxide. Remember that the chemical formula, right, for hydrogen peroxide is H2O2. Now when you learn in Chapter 3 about naming, you'll see that hydrogen peroxide is just a common name for hydrogen peroxide. And actually, the most correct way to say hydrogen peroxide would be dihydrogen dioxide. Anyway, we'll get to that in Chapter 3. So hydrogen peroxide at room temperature is a liquid, and it's composed of hydrogen and oxygen atoms. And in this case, in the case of hydrogen peroxide that you buy at the store, it's not pure hydrogen peroxide, it's mixed with water, so it's a mixture. And so we want to think about how to classify substances in addition to their state and their makeup. So that's what we'll talk about next. We'll talk about it in the slide after this. Sorry. So let's just talk about solids and liquids and gases just for a second. So over here in the right, you can see that there are 3 different representations of water. One is in the solid state, one is in the liquid state, and one is in the gas state. So in the solid state, the molecules are close to one another. They are closely packed. In the liquid state, the molecules are spread farther apart. And in the gas state, they're spread the farthest apart. So we expect that when we show you these different depictions of matter, you'll know what state it's in. So use this sort of as a frame of reference. So in addition to that, I want you to know a couple of other things, right? That gases and liquids, they are compressible. They can take the shape of whatever container they're in. In contrast to solids, which don't take the shape of the container. And then since the atoms are so closely, or molecules are so closely packed together, they're not very compressible. And in the true scientific sense of the word compressible, there's a little bit of a, I mean, you can measure it a little bit, but in general, they're just not compressible. One thing that's not depicted in these static representations of atoms and molecules is that they are constantly in motion. So the speed of gases is greater, though, than the speed of liquids. The speed of liquids is greater than the speed of the molecules in solids. So in solids, they're just sort of vibrating next to one another. In liquids, the molecules or atoms can move around one another, sort of slide over one another. And then in the gas state, there's collisions, and there's a lot of very fast, freely moving particles. It's important to have that idea of matter as well, even though, you know, we're always using static representations of these things. Okay, so I want you to be able to classify matter. We can classify matter in 2 major ways, in whether or not matter is composed of a pure substance or whether or not it's a mixture. And if something is a pure substance, it can either be considered an element or a compound. So an element cannot be broken down into simpler substances. So a good example of an element is helium. And then you should notice here that this particulate representation of helium is in the gas phase. So right, these molecules in this depiction are spread far apart. So you need to, when you see a depiction like this, have that understanding. Okay, so another example of a pure substance is water. In contrast to helium, however, water is a compound. So water is composed of hydrogen and oxygen atoms. So it can be broken down into its individual elements. So we consider water a compound. We also will call water a molecule. And then if matter is not a pure substance, if it's a mixture, then we can classify it in 2 ways. If it's uniform, then it's a homogeneous mixture, and if it's not uniform, it's called a heterogeneous mixture. So let's look at heterogeneous and homogeneous mixtures a little bit more closely. Okay, so let's look at the homogeneous mixture first. So this is composed of, right, 3 different kinds of molecules. these molecules are evenly distributed throughout, and so it's evenly mixed. In contrast to a heterogeneous mixture, for example, wet sand. So in this wet sand, you have something here in the solid phase, and then a liquid phase on top of that. The things in the solid phase are different than the things in the liquid phase. So the molecules in the solid phase are different molecules from those that are in the liquid phase. So we consider that a heterogeneous mixture. So we've been talking about changes in state. So anytime something changes in state, it's a physical change. So it doesn't change the composition of the substance. So this is a state change. Also, things like tearing or mechanical changes, as long as the composition doesn't change, those are physical changes. Like, for example, if I took a piece of paper and I ripped it in half, I would have now not one thing but two things. Each one of those things, though, would be composed of the same thing, both composed of paper. So in addition to physical changes, there are chemical changes. So if something undergoes a chemical reaction and the composition of that substance changes, it's a chemical change. So all matter can be described by both chemical properties and physical properties. So physical properties are ones that a particular substance has without changing its composition. So, for example, if we think about water, water has a particular melting point, and it also has a particular boiling point. And both of those properties are physical properties. Chemical properties, on the other hand, require a chemical reaction. So examples of chemical properties would be like corrosiveness or flammability, that sort of thing. So probably the most important part of this review are these slides. How do we expect you to use this information, right? So we expect you to be able to look at these depictions and determine whether or not it's a pure compound or it's a mixture, and whether or not something is undergoing a physical or chemical change. So let's look at this first thing here. So here we have something on the left here. This set of molecules, these four molecules, they're close together. So I would assume that these are molecules that are representing something in the liquid state. There's only one type of molecule, so it's a pure substance. So here we have a pure substance in a liquid state. Some sort of change happens. As a result of this change, we still have these four molecules, and they are still the same. I mean, they have the same chemical composition, but they're just spread farther out. So I would describe this as a physical change. This is a physical change. We have a pure substance on each side, and the pure substance is a compound. So let's look at the next example here. So in this next example, we have not one, but two different compounds. And so we have something that's a mixture. These molecules are spread evenly throughout here. So this is a heterogeneous mixture. So it's a heterogeneous mixture in a gas phase. Some sort of change happens, right? We have a change. And now, even though we still have two different compounds on the right-hand side, they have a different chemical composition. So this is reflective of a chemical change. These two molecules are representing carbon dioxide. So remember, oxygen is represented as red and carbon is represented as black. So this carbon dioxide, there's only two of them. It seems to be evenly distributed. So we have both on the right-hand side and the left-hand side here a heterogeneous mixture. All right, that's in the gas phase. Okay, so let's look at C. C, we have water on the left-hand side here. These water molecules are close to one another. So this is a pure substance in the liquid phase. Some sort of change happens. As a result of this change, these molecules are spread farther out, but it's still water. So since there's no change in chemical composition, but there's a change in the proximity, how close they are to one another, we're going to say that this is a physical change. We have a physical change of a pure substance. That's a compound. Okay, so let's look at another example. So you should ask yourself, what is this? Okay, so you have a mixture. There are two different things here. This is one substance, and then this is another substance. These two substances are not evenly mixed. So this is a heterogeneous mixture. Let's look at this other example. In this other example, there are two substances, right? So we have this substance and this substance. In actuality, we have water right here. This is depicting water. And then this other molecule is actually ethanol. So we have this water-ethanol mixture. Ethanol, there's 3 ethanol molecules here. They're spread fairly evenly throughout. So this would be an example of a homogeneous mixture. And I would describe this as something probably in the liquid phase. Okay, let's look at one final example. So for this example, I want you to determine whether or not it's a physical or a chemical change that occurs. So let's look at the first one. So in this first example, you have a molecule over here on the left, you have a molecule over here on the right. They're the same molecule. On the left, this is depicting something that's a solid. Here on the right, you have that same material that's a solid, that same compound, but now you have some water molecules around. So this is depicting dissolving. Dissolving results not in a chemical change, but in a physical change. So let's look at the next example. In this next example, you have some sort of, on the left, hydrocarbon. This hydrocarbon is in a liquid phase. So the hydrocarbon just means something that contains only hydrogen and carbon. So carbon, right, is these black spheres. The hydrogen is in the white spheres. And then on the right-hand side here, you have carbon dioxide and water. So you have a different chemical composition. So this is going to be a chemical change. Now, you should ask yourself in the right whether or not this is depicting something in the gas state or something in the liquid state. It's depicting something in the gas state. And you can see these little shadows here by the molecules. So a lot of times to represent the motion of matter or of molecules, particularly in the gas state where they're moving really fast, people try to put this little shadow business in there to illustrate or indicate that there's some speed. So you should know that that's what that means. So in addition to getting yourself oriented to matter, you need to get yourself oriented to solving quantitative problems. The first step for that is to understand the SI base unit. So, we use the English system. We're always going to have to convert to the SI system. You should know what... Now, listen, in chemistry, we don't really use luminous intensity. I have never solved a chemistry problem using that. So, it's up to you whether or not how familiar you would like to be with that. But these SI base units, you should know the unit, what quantity it's measuring, and then also the symbol. This is going to help you understand how to solve your chemistry problems. So in addition to SI units, we use Fahrenheit in the US. We're always going to have to convert degrees Fahrenheit to degrees Celsius or Kelvin. So you should have a sense of how to do that. Well, you should have a sense of how these scales differ from one another, but you should also have a sense of how to calculate that. So you should know both of those formulas. It's a rare case, but sometimes you have to go to Fahrenheit. And so remember, we did this in class. Fahrenheit is equal to 9/5 times degrees Celsius plus 32. You should be able to do that algebra really easily. So let's practice a type of temperature conversion that you'll have to do. Okay, so you'll need to, like I said, be able to convert between degrees Fahrenheit, degrees Celsius, and Kelvin. So let's just do one conversion of degrees Celsius to Kelvin. So you should probably pause this and make sure that you can do it on your own. So the first thing you want to do is write the formula. So kelvins are equal to degrees Celsius plus 273.15. So you can just sub in 5.5 times 10 to the third. For this, since we don't need to really keep track of units, I feel like they can kind of be confusing to have the degrees Celsius there. So plus 273.15. Okay, so you want to plug this into your calculator. You get 5,773.15 Kelvin. Now, I expect for you to be able to always do sig figs correctly. So we're doing an addition problem here. This number here that's given to you in the problem has one place past the decimal. But it's written in scientific notation. So it's really indicating that there are only two significant figures here. So your answer can only have two significant figures. So the correct answer would be 5.8 times 10 to the third. Alright, so in addition to you knowing the SI units, you need to be familiar with the prefix multipliers. So for example, and remember the prefix multipliers are just words that indicate the power that something is raised to, or the amount. So for example, kilo means 1,000 or 10 to the 3. So how I expect you to be able to use this is, for example, if you have 1.2 times 10 to the 3 grams, I expect you to see this and be able to rewrite it as 1.2 kilograms. So in addition just to simply writing them in we're using the prefix notation, you need to be able to use these something like 1.2 kilograms and be able to convert from kilograms to grams or kilograms to milligrams or that sort of thing. And when you do this, I prefer that people go through the base unit. And so the base unit just means whatever SI unit that you're using in your calculation. And let me just show you what I mean by that in this next problem. So if you have a book that has a mass of 2.52 kilograms and you want to find that mass in milligrams, you're going to set this problem up by going from kilograms to grams to milligrams. So push pause, make sure you can solve this on your own. I'm going to solve it right now. So if you have 2.52 kilograms, for every 1 kilogram, you have 10 to the 3 grams. And for every 1 gram, you have 10 to the 3 milligrams. So the way to remember about this is just to think about whichever one is bigger or smaller. So kilograms are big, so a lot of grams are going to make up a kilogram. So that's why I know, right, that it's 10 to the 3 grams for every 1 kilograms. Similarly, there are a lot of milligrams that make up 1 gram. So a gram is bigger than a milligram. So I know that I have 10 to the 3 milligrams for every 1 gram. You're going to want to make sure that your units cancel out. Kilograms cancel out, grams cancel out. You're left with milligrams. And you want to punch this into your calculator. You're going to get 2.52 times 10 to the positive 6 milligrams. Now, you might be tempted to convert straight from kilograms to milligrams, and I'm just going to say that when we get into more complicated chemistry problems, I'm going to recommend that you don't do that, that you always go through the base unit. I think is a better problem solving approach. In addition to using SI units, everything, I want you to be able to not only understand density, like what density is, but to use density as a conversion factor. So density, right, is just how much stuff is in a particular space. So density is mass per unit of volume. So mass divided by volume. Remember that the density units are grams per liter, grams per cubic centimeter, grams per milliliter. And that 1 cubic centimeter is equivalent to 1 milliliter. Always remember that. Density is an intensive property, so it's independent of the amount of substance you have. Mass and volume, on the other hand, are extensive properties, so they depend on how much you have. So I would be familiar with these words. They show up a lot in on chemistry exams and on the chemistry ACS exam, but you should just know the difference between intensive and extensive properties. I feel like it's always used, people tend to forget it, so it's used sort of as a trick, so I would remember it if I were you. Okay, so you need to be able to use density as a conversion factor. There's one typo in this slide, so this should just be volume in cubic centimeters. again, I would pause this, confirm that you can solve a problem like this. At the bare minimum, you need to be able to solve problems like this. Okay, so diamond has a density of 3.513 grams per cubic centimeter. The mass of diamonds is often measured in carats. 1 carat equals 0.2 grams. You want to find the volume in cubic centimeters of a 1.5 carat diamond. So you're given the mass of the diamond in carats. You're given density. And you're given a conversion factor, a factor to convert carats to grams. Okay, so to solve this problem, you're going to start with the mass in carats. You want to use this conversion factor to find the mass in grams. And since density is provided, you can use the density to go from the mass in grams to the volume. So that's our problem-solving approach. So I'm going to start with 1.50 carats times, for every 1 carat, there's 0.2 grams. And for every 3.513 grams, there's 1 cubic centimeter. I'm going to check and make sure all of my units cancel out. Carats are on top, carats are on bottom, grams on top, grams on bottom. I'm left with cubic centimeters. I double check and make sure that's what I want to find. Yes. I'm going to punch this into my calculator. 1.5 times 0.2 divided by 3.513. So I get 0.08539.7 cubic centimeters. We need to put this in the correct sig figs. 1.50, that has 3 sig figs. 0.200, 3 sig figs. 3.513, 4 sig figs. So my answer can only have 3 sig figs. So my answer is going to be 0.0854 cubic centimeters. All right, finally, I want you to be able to appropriately convert cubic or squared volume. Okay, so just for example, if you have 1.36 times 10 to the 9 kilometers cubed of water, and you wanted to find this amount in liters, find in liters, and I gave you one conversion factor. If I told you that 1 liter is equal to 10 to the minus 3 cubic meters, I would expect people to be able to solve a problem like this. So if you can go from cubic kilometers to cubic meters, then you have a conversion factor to go from cubic meters to liters. So you have this step right here, right? But then the one that's tricky is this step. And you just have to remember to cube your conversion factor. So let's set this problem up. you have 1.36 times 10 to the 9 cubic kilometers. You know that for every 1 kilometer, you have 10 to the 3 meters. Since these units aren't squared, you have to cube each, like that. And then you have your conversion factor that you can use. You know that 10 to the minus 3 meters cubed is equal to 1 liter. So you want to check and make sure that your units are going to cancel out. Yes, those units will cancel out. Meters cubed, those cancel out. You're left with liters. And so put this in your calculator. This will be a really good test to make sure you know how to enter things into your calculator properly. If you don't, you need to ask someone immediately. Do not wait. It'll mess you up on your test. So I get 1.36 times 10 to the 21 liters. Let me write that more clearly. Okay, so you should be able to solve some problems like this. And if you can't, if you could not solve this problem on your own, then you need to come to my office hours or Katie's office hours or go to the resource center, okay? Okay, so just to be clear about the expectations for Chapter 1. Expect people to classify matter, know what state something is, the composition, both in terms of, like a description. For example, if you burn something, right, you know that that's a chemical change, or if something goes from a solid to a liquid, you know that that's a physical change, a change in state. But I want you to be able to do that by looking at those molecular representations, so that the representations at the particulate level. Convert between English and metric system units. Apply and use the prefix multipliers in both of the ways that I talked about. To convert between different temperature scales, use sig figs and scientific notation correctly. This says use volume as a unit conversion. I mean density. And also with density, or with volume, to convert using volume units correctly. And then do sort of multi-step dimensional analysis problems. So those are the expectations for Chapter 1. So I just want to be clear what they are before you have your test. And I'll make a video for Chapter 2. And if you have any questions about anything in this video, send me an email, come to office hours, ask in class. I want people to do really well on their exam. I want you to succeed in this class.